In this video, we're going to try to show that the path of the planet is going to lie in some plane. And we're going to do that by showing that r crossed with v is constant, so that it's always going to be this vector b. Remember, we defined in the last video that b was r naught crossed with v naught, which made it the initial distance times the initial speed times k. It was pointing straight up. Okay. We're going to show that that's what we always get at any moment in time. Now, before I demonstrate that, let's talk a little bit about why it is that that would then be equivalent to saying that the path is always going to be in some plane. Now, as we've set up our coordinate system, that's going to put it so that the object is always in the xy plane. So we chose our coordinate system nicely so that we could say the plane we're working in is just the xy plane. Well, if this is the xy plane, and r cross v was constant, it was always this vector b that we're saying is pointing straight up, then that's telling us that r and v are always orthogonal to b. Because remember, the cross product is going to be orthogonal to both of these components. Okay. So this vector that's pointing straight up is always going to have to be orthogonal to my position vector. And my position vector is, of course, going to be non-zero, because if we were to fall into the sun, well, we would cease to exist, and therefore we would cease to care about this problem. Okay. All right, so if I have an r vector that's on the xy plane, it's definitely going to be orthogonal to this vector b, since it's just a multiple of k. If I have an r vector, a position vector, that did not lie on the xy plane, now when I draw it in standard position, its tail is at the origin, it's going to have some vertical component to it. So maybe it points upward, possibly it points downward, something like that. It's not going to be orthogonal to this vector b that points straight up. So if we can show that this is constant, we will show that our position vector will always have to be, as we've set up this coordinate system, in the xy plane, so that we can work just in a plane. All right, so how do we demonstrate then that this is constant? Well, if things are constant, their derivative is zero. So I'm going to take the derivative of this cross product. Remember, position and velocity are functions of time. I just haven't bothered to write in it r of t and v of t. And we have a rule for the cross product that says I can say this is going to be the derivative of r crossed with v plus r crossed with the derivative of v. So it's sort of a generalization of the product rule across the cross product operation. Now, the derivative of r is just v. That's going to be my velocity. So this first factor is v crossed with itself. Well, that's going to be zero, because anytime I cross a vector with itself, I'm going to get zero, because remember, the cross product, the magnitude of the cross product rather, is going to be this magnitude times sine of the angle between these vectors. But the angle between v and itself is zero. So I'm getting a vector of zero magnitude, I'm getting the zero vector. In fact, anytime I cross parallel vectors, they don't even have to be identical. Anytime I cross parallel vectors, I get zero. So what's the second factor then? Well, this is going to be r crossed with a. The derivative of velocity is acceleration. But here, I can actually use Newton's second law, that the force is equal to the mass times the acceleration. Okay. So the force of gravity that I have is going to be the mass of the planet times the acceleration. Now, this is a positive scalar, so that says that acceleration and this force of gravity point in the same direction. But I know what direction that is, because the force of gravity that the sun is exerting on the planet is an attractive force. So if this is my position vector here, pointing from the sun to the planet, the acceleration, which points in the same direction as that attractive force, points in exactly the opposite direction. It's pointing from the planet to the sun. So, because this points in the same direction as the force, which is the opposite of the direction of the position vector, these two vectors here are going to be parallel, and therefore this is also going to be 0. So the derivative is 0 plus 0, which is 0. If the derivative is 0, we know we have a constant. But we know what that constant is because we know what it was at time 0. At time 0, it was this lovely vector b. So b is what we always get, and that tells us that we are going to be working in a plane. That's fairly nice. So I know I'm working in the xy plane. Now that doesn't mean I'm going to abandon 3 space, because it turns out that this cross product and this vector b are actually going to be fairly useful. So I know that my curve lies on the xy plane in 3 space. So all of my vectors will be in 3 space. But I basically know if I'm writing my r of t at any moment in time, it's going to be some copies of I plus some copies of j, or if I wrote it in component form, I'd have something in the first and second component, but my third component is always going to be 0. So I'm working in the xy plane in 3 space. Now what we're going to do is we're going to introduce, we've already sort of introduced r, which is the distance from the object, and I'm going to also introduce theta. So I can describe a point in the xy plane in terms of r and theta and z, but the z value is just 0. Okay. And what we're ultimately going to show is that the path of any object that's caught in the gravitational field of the sun, that doesn't get caught so much that it just goes straight into the sun and implodes, is going to be some sort of a conic section. Now for planets, that conic section is an ellipse. For an object that doesn't get caught by the sun, that conic section could be a parabola or a hyperbola. So that would be an object where if this is the sun, the object is traveling along, the gravitational field starts to pull it in, but then it manages to escape and turn away, and this path would either be a parabola or some portion of a hyperbola. Now, that's why it's going to be so useful that we're going to introduce our polar coordinates here, because all conic sections, whether it's an ellipse, a hyperbola, or a parabola, they have essentially the same format for their equation when we work in polar coordinates. Their equations look different in rectangular coordinates. They look very similar in polar coordinates. In polar coordinates, a conic section, excluding a degenerate ellipse, which would be a circle, a conic section looks like this. R is equal to E times D. These are going to be 2 positive constants. I'll talk a little bit more about them in a moment. Over 1 plus or minus E times cosine of theta. If I had a sine theta here instead, that would also describe a conic section. So there's a few variations. I can have either a plus or a minus, and I can have either a sine or a cosine. D is a distance that we have. So D is going to be a positive constant. And E is also a positive number. E is our eccentricity. And the eccentricity, the value of E, determines which type of conic section I have. So if 0 is less than E is less than 1, I'm going to have an ellipse. If the eccentricity is 0, it's a degenerate ellipse, which is a circle. And we're saying we're not going to get that. I'm not assuming that we're not going to get that. We're just going to see that we don't get that. Okay. If E is equal to 1, we would have a parabola. And if E is, greater than 1, we would have a hyperbola. Okay. So it's kind of nice because these assumptions that we've made, that we're making for our planet, would also be true for objects that get pulled towards the sun but don't get caught in its gravitational field and move away, so that they move away in a parabolic or a hyperbolic path as well. So we're just going to get that we get a conic section. And then how do we know that for planets it's actually an ellipse? That's based on observation. That's based on the fact that we actually have seasons, so that we can see that we're repeating a pattern rather than initially getting closer and then getting further and further away. Okay. All right, so that's where we'll pick up in the next video.